These questions, this is in exercise 3D, and this is question 5. These are all about using the identities that you know for trig to try and simplify equations over a particular interval. So I've put just underneath here all the different equations that we've looked at so far. So if we have a look, you can see you've got your double angle formulas, your compound angle formulas, and then these ones here are derived from your Pythagorean identity, which is sine squared x plus cos squared x equals 1. So looking at I as the question here, you can see you've got a whole mix of stuff going on, so it's kind of hard to tell which one to go with here. What sticks out at me is I've got a tan, I've got a cosec, and what sticks out to me there is these ones here, because these are the ones that deal with cosec, with tan, with cot. So there's a couple of ways that you could go with this. What I'm going to do is I'm going to look, I can see there's a tan squared x here, and if I write this out slightly differently, you can see we've got 1 on tan x is cot plus 3 tan x equals 5. Now cosec x is over sine, so it's 5 over sine x. Now I can see here that if I multiply both sides by tan, what that's going to do is it's going to give me a 1 here where I'd like to have it. It's also going to give me a tan squared. So if I multiply both sides by tan, I'll actually just add that in a different colour. So I'm going to have tan x on the top, tan x underneath. This will become tan squared x. So I'm multiplying everything by tan x. Here I'm going to have 5 on sine x times tan x. Now the reason I've split that up is so that you can see on the next line, I'm going to do a bit of cancelling. So these two things are the same, which means that they cancel down to 1. This is going to be still 3 tan squared x. Now here I'm just going to expand what tan actually is. Remember that tan x is sine over cos. I always think of tan as actually being sine and cos. I don't think of it as being a different thing. And by thinking that, now what I can do is I can see I've got a sine on the top and on the bottom. Okay, so what that's going to do for me is help me with the next part. So we've got 1 plus 3 tan squared x equals, this is going to be 5 over cos, and remember that being over cos is sec, so this would be 5 sec x, like that. You can see we're kind of close to where you'd want to be. What I can do here is at least eliminate tan squared x by using this identity here. Okay, so it's always a good idea to just say what you're going to use, using 1 plus tan squared x equals sec squared x, like that. So what we're going to do, I'm just going to pick up this line here and move it to the next page. Okay, so what you want to do is now, the red pen, say what we know, and we know that, we know this, which implies we can solve that for tan squared x, so sec squared x minus 1. So that means that we can now substitute. Oops. And doing that, I'll go back to my blue. We've now got 1 plus 3. Now in place of tan squared x, I'm going to put this expression here. So that's going to go in here. So we've got sec squared x minus 1 equals 5 sec x. And next line we've got 1. I'm just going to expand this out so we can see what we're dealing with. So we're getting closer because we're now minus 2. We're now eliminating trig. So the next thing that we might want to do here is look at that expression and think, oh, what does that look like? Now you've got one term that's squared, one term that is just to the power of 1, and one term that doesn't have a sec in there at all. This is actually a hidden type of equation. What type of equation is it? Oops. It's a hidden quadratic. Okay, So all we're going to do, I'm going to let sec x equal, you can let it equal whatever, I'm just going to let it equal a. So now what we have, we've got negative 2 plus 3a squared, because sec x is a, equals 5a. Going to rearrange it so we've got everything onto one side. So 3a squared minus 5a minus 2. All I've done is just take the 5a to this side and divide everything by 3, just so that now I'm dealing with everything with a 1 out the front of the a squared. So what we'd want to do with that is to try and factorise it. Okay, so we could complete the square. So we're going to have a squared minus 5 over 3a. Halve this would be 5 over 6. Square it would be 25 over 36. We add it. So we've got 25 over 36. We subtract it. Oops, excuse me. And then we add on the rest. Now because this is over 36, it makes sense to really multiply the top and the bottom here by 12. So 12 would give you 36 on the bottom, and 12 times 2 is 24. So it just gets everything sort of looking a bit easier to deal with. So now what we're going to do, this is a perfect square. It's going to be a minus the square root of this term, 5 over 6 squared, minus here, this is going to be quite ugly, frankly, but that's all right, 49 over 36. Okay, we're nearly done. You can see that that's actually a nice perfect square there. I'll put this on the next page. When you're taking things outside a perfect square, so these things here, as long as it's a negative, you can pick that up and take it inside. But when you take it inside, it's always plus and minus the square root of that thing there that goes inside the bracket. So we can take that inside now. So we've got a minus 5 over 6. Square root of this is 7 over 4, so we're going to have 7 over 6, excuse me. So we're going to have plus 7 over 6, and then we'll have minus 7 over 6. So that's this part here, the 7 over 6. Square root of 49 is 7, square root of 36 is 6, equals 0. Just simplifying that, we've got here negative 5 plus 7, so that's going to be plus 2 over 6. And this will be a 5 and 7 minus 12 over 6. And then just going to simplify that. A plus a third, a minus 2. Okay, so there are solutions. That's been factorised now. Okay, so if we go back, we know that what we had there was sec x equals a. So we can go back here and we can actually put that sec x back in. And because we're trying to solve these expressions here, both of these expressions can be solved. We need to solve over a particular interval as well, and the interval is the one that's given in the question, solve over 0 to 2 pi. So we can solve over 0 to 2 pi. Two expressions. Expression 1 is sec x equals 1/3. Okay, remember that sec is 1 over cos, which implies that cos x equals 3. That's the first one that you have to solve. And then the second one that you have to solve is sec x minus 2 equals 0. Should put a sign there, negatives. Okay, so now looking at this, we've got sec x equals 2. Remember that sec is 1 over cos. So that's going to be flipped over to give you cos x equals 1/2. So we've got two solutions there. This one is non-standard. So with this one we can actually solve for x. So when x is 1/2, and remember if we've got a triangle, cos is the adjacent one, it's the one right next door, so it's pi over 3. So our answers would be pi over 3, and also thinking about the unit circle, they would be there and there to give us a positive value for x, so, and for cos. So there would be pi on 3 and minus pi on 3, which is the same as 5 pi on 3. So they'd be our solutions there for x. For this one, you'd need to use your calculator to solve this. Look at the other part here that we need to solve. We don't know this, so we're going to use the calculator. So I'm just going to get CAS. So it's cos x equals -3. Now you might have already thought about what the answer is to that. Oops, tapped in the wrong thing. So we've got cos x equals -3, and we're going to solve that for x. And you can see that it comes up with false. Now if you think about it, remember that we're dealing with the unit circle. There's no way that cos can be bigger than -1. Okay, -1 is it's bound to the left and 1 is it's bound to the right. So this is actually not a true statement or not a true equation. It can't be solved. There are no solutions. So if we go back again to our working, we can actually write there now that for this part here, there are no solutions. That does not work for our question. So all we're left with then is this. So because cos x equals 1/2 was our other solution, this one here, that actually did give us 2 solutions which were okay. So that means for this question, our final solution is just those 2 that we found from cos x equals 1/2, or from sec x equals -2, which was x equals pi/3 and 5 pi/3, both of which are within the interval that we needed, which is the interval between 0 and 2 pi. So the key with this one, and why it's so difficult, is that there are quite a few steps to it. Looking back, the first thing that we did was identifying it's probably one of these. You could see there's a tan and there was a cosec in there, so it links to this. You could have actually made it equal cosec squared by multiplying everything by cosec and working through this one too. I went with tan squared x, multiply everything by tan x, and then work through it. Keep with it, okay, stick with it and see where you end up. And you can see when things start to cancel, that's probably good. Here, taking this expression now and eliminating one of the trigs so you're not dealing with 2 things, you know what tan squared x is. You can express that in terms of sec squared x. So it makes sense to have everything in your expression with just sec, whether it's squared or whether it's the power of 1. This is then a hidden quadratic, which you can solve. We used completing the square. You know, straight up at this point, you could put this into your TI so that you don't have to do all of the work. But we just did this, completing the square by hand to get our 2 solutions for sec x, and then solving them. Remembering that sec is 1 over cosine, so we'd have to flip these 2 answers to get a 3 and to get a positive 1/2, and then solving for x to get our final solution in the particular domain that we required.